Say a six-sided die is rolled 50 times and produces a 1 8% of the time. Lots of numbers rolling around there. Construct a confidence interval on the proportion of times that the die produces a 1. We're going to start off and say if I need to construct a confidence interval, I do that by taking a point estimate, adding and subtracting a margin of error. So let's start off with what is the point estimate. This is a proportion problem. That's clear in the setup of this because I'm saying that I've done something and I have a certain number of successes and a certain number of failures. I'm successful 8% of the time, I'd fail 92% of the time, right? And when that's that type of setup, we say we have a proportion problem. And so my best point estimate for a population proportion is the sample proportion. Sample proportion p hat is just going to be take that 8% of the time I was successful in my sample and convert it to decimal. So I start off with my point estimate, p hat equals 0.08. Once I have the point estimate, then I need to find the margin of error. The margin of error, as we discussed, is found by taking the appropriate critical value, multiplying it by the standard deviation of the point estimate. So we're going to take from that formula that we were just given and say that margin of error is equal to z times square root p hat q hat over n. And now I just have to plug in the right numbers. Here's the catch. Make sure that you plug in the appropriate critical value. We don't plug in the confidence level. We don't plug in the significance level. Plug in the appropriate critical value. Okay. And this might be the point of the problem where you notice we weren't given a confidence level. And if that's the case, we are going to assume 95% confidence. So a lot of times the problems like construct a blank percent confidence interval. That confidence level will be written in the problem. Sometimes it won't. If we are not given a confidence level, we are going to assume 95%. We're going to assume our significance level is 0.05. And so if we have a 95% confidence level, that corresponds to a z-score of 1.96. Then I just plug in that p hat that I've already found of 0.08 and is 50. Notice the information about whether it was a 1 or a 2 or a 3 doesn't matter what we rolled. That's irrelevant. The fact that there's 6 sides in the die, also irrelevant. Go ahead and just finish that math off and we can get an answer of 0.075 for my margin of error. And once I have that, I can find the confidence interval by just adding and subtracting that margin of error to the point estimate. So I'm going to take that 0.08, I'm going to subtract 0.075, and I'm going to add 0.075, and I can get the interval given below. Now, as we talked about last video, we don't just report the confidence interval, we write out a sentence. That sentence is going to take shape like we had earlier in this set of notes where we said we are blank percent confident that the interval between blank and blank contains the parameter of interest. So we're going to say we're 95% confident the interval between 0.005 and 0.155 contains. And remember, we wrote down the parameter of interest in brackets, but I made the comment, I said we're not going to write the parameter of interest. We're going to actually write out what the parameter of interest is. When we do that, we have 3 things that we need to write. The first thing is we need to write some word that indicates that we have a parameter. That could be true, real, known, all, actual, lots of different options for that. But some population-like word to indicate to me that you are telling me that you think the parameter falls in the middle of this interval. Why is that important? I want to make sure you understand we don't think that the statistic falls in the middle of that interval. Why is that? We know the statistic. We don't need to have a confidence interval on the statistic, right? And this is where we talked about from the beginning of the course, making sure we know the terminology here. When I say that the statistic is p hat, the statistic is 0.08. I know exactly what it is. We would never build a confidence interval on a statistic. It is what it is. It's 0.08. I don't have to guess at it. The whole point of the confidence interval is I don't know what p is, but I think I can build an interval that probably contains it. Right? And so that's when we need to make sure we indicate when we write out what it contains, you need to include a parameter word, all real, known, population, true, actual, whatever it may be. So that's the first thing. Then the second thing is you need to tell me what metric we're using, right? And for now, we're just going to say, hey, we've got proportions that we work with and we've got means that we work with. Could we do this on medians? Yes, we could. Could we do this on standard deviations? Yes, we could. Could we do it on variances? Absolutely, right? We're not going to do that in this course, but we could do it on any metric. Okay, but the metrics we're going to focus on are proportions and means, so you need to write one of those words depending on which one it is. And then you need to tell me the context of the problem. Don't just say we're 95% confident the interval from blank to blank contains the true proportion. True proportion of what? Okay, so make sure you indicate what it actually is in the context of the problem. And then one last note, if you use the word proportion, you should write your interval out in decimal. If you use the word percentage, that's totally fine. You should convert your decimals to percent. I'm going to leave these in proportion because why do I want to convert those numbers to percent? And so I use the word proportion in my one sentence write-up. We're 95% confident the interval from 0.005 to 0.155 contains the true proportion of times that this die produces a 1. Every time we do a confidence interval, we're going to do 3 things. Number 1, we're going to find the interval. Number 2, we're going to address some claim about the interval. And then number 3, we're going to check our assumptions and address the validity of our results. Now that we've found the interval, we've written our sentence out, we're going to move on to the claim part. This one says, address the claim that the die is unbalanced. Every time we address a claim, the easiest way for me to think about how we want to do this is you want to say to yourself, is the claim always true, sometimes true, or never true? Okay, we have to think to ourselves, is it possible, or is it always going to happen, or is it never going to happen? Okay. Remember that the interval is the set of values that I think contains the parameter. Now, I want to touch back on something we talked about last video, which is, remember, when we say 95% confident, or any percent, in this case 95, we're confident in the process that if we were to do this a bunch of times, 95% of the time it would work and we would be capturing the parameter. 5% of the time, though, that means it wouldn't work. We have no confidence in our one interval. We don't know. It either got it or it didn't. We might have been unlucky, but I want to make sure we understand when we address the claims, we're going to assume that we didn't get unlucky. Okay, so when we write out our statement, we're 95% confident, we need to understand that we don't know anything about our one interval. It might have gotten it, it might not have. What we're confident in is the process that in general this thing works. And so when we address claims, we're going to address them under the assumption that our process did work like we hoped it did. And what we're going to do is we're going to say, I think that P is somewhere between 0.005 and 0.155. You have to understand that's the crux of the confidence interval. I think P, the true proportion of times that this die rolls a 1, is somewhere between 0.005 and 0.155. Don't know where in there. I just think it's in there. And so you can think to yourself, it's possibly 0.007. It's possibly 0.012. It's possibly 0.085. It's possibly 0.134. It's possibly 0.101. There's all these things that are all possible. It's somewhere in there is what I think. And that's how I'm going to address the claim, by assuming it's one of those values in there. So this says address the claim that the die is unbalanced. And this is where we have to do a little bit of critical thinking. If the die is balanced, I would get a 1 on a 6-sided die 1 out of 6 times. 1 out of 6 converts to decimal, 0.167. And so if I'm saying is the die balanced or unbalanced, if P is anything that's between 0.005 and 0.155, could be any of those numbers, but don't know which one, I would have to say, is it possible that this die is balanced? And you would say, well, if I have my possible values between 0.005 and 0.155, you may want to draw a number line. Draw out your number line and say it's somewhere between 0.005 and 0.155. It's anywhere in there. But then I said 0.167. That's what I need for unbalanced. That's not inside that interval, is it? You'd say 0.167 isn't inside the interval, so it's not possible for the die to be balanced. And so I'm going to say that I can conclude that the die is unbalanced. Why is that? Because the value in question doesn't lie in the interval. Now, we will see other examples that will hammer this point home, but I want to make sure that we understand that on these types of problems, we cannot just shortcut to is the value in question in the interval or not, because there are times when we will say it is in the interval and we can conclude something, and there's times when we say it's not in the interval and we can conclude something. So we can't just try to make it a shortcut type situation. We have to use critical thinking and try to assess based on the understanding that the interval is the set of possible values that I think contains the parameter. And then I have to say, what about my claim? Does this always agree or sometimes agree or never agree? Okay. Last thing we're going to do is check our assumptions. Always, 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 first thing we're going to do is check our sampling methodology. Is our sampling sound? Do we have any of the biases that we talked about way back in chapter 1? In this case, there's literally one sentence of problem, so there's nothing I could say about the sampling methodology, about it being bad or having a bias. There's nothing really happening here, so I'm going to say, yep, we're good there. Again, we're not going to make something up. We're going to check to see if there's a problem, but if there's no problems that jump out at you, we're going to say we're fine. And then we have to check our mathematical assumptions. That's the idea that we have to make sure that X is binomial, we have 5 failures, and we have 5 successes. And I would say, yes, X is binomial, and we have enough failures. However, we only have 4 successes. And you say, how did I figure out that we only had 4 successes? Well, our number of successes is going to be equal to n times p hat. Notice in this problem, I've been given n and p hat. And so I know because p hat equals x over n, if I'm trying to solve for x, again, I multiply both sides by n. X equals n times p hat. If I take n, which is 50, and p hat 0.08, multiply those together, I get 4. There were only 4 successes, and that's not good. So I have an assumption that I need to check, and it doesn't hold up. So anytime we're addressing our assumptions, there's 3 pieces. Number 1, let's check our sampling methodology. Do we have any biases? Did we sample awkwardly? Are we representative? Need to make sure that our sampling's good. Then number 2, we check our mathematical assumptions. Just like we did in chapter 7, we're going to say for proportion problems, we need X to be binomial. We need to check if we have 5 successes and 5 failures. Remember, for our mean problems, it's going to look like the mean problems we did in chapter 7, where we're going to try to see, is X normally distributed, or do we have a big enough sample size for central limit theorem to hold the same concepts we talked about before. And then after we've done that, there's a third part, and that is actually address the validity of your results. Don't forget to answer the question. Questions that address all assumptions and the validity of your results. Are your results valid? And the answer to that question is your results are as valid as your assumptions. If your assumptions are valid, your results are valid. If your assumptions are really good, your results are really good. If your assumptions are really bad, your results are really bad. It's directly proportional. Okay? And this is where there's a little bit of nuance, and that's okay. But we're going to say my assumptions are not 100% there, but they're close. And so my results might be a little bit off. Or we're going to say my assumptions are really far off. And so I don't think these results are very good. We're going to give an honest assessment of our results based on what we think about our assumptions. Okay, so there's a lot of right answers at this point. Notice I've got good sampling. That's one thing I've got to consider. If anything falls apart here, it's a problem, right? This is pretty good. This is good. This is good, this is not good. It's off by 1. So it's one of those where I might have a little bit of an issue. If this is off by more than 1, I have a bigger issue, right? So I have maybe a moderate issue, a mild to moderate issue here. If this is 4.9, I'd say that's a very minor issue. If it's 4, it's a little bit bigger. If it's 2, it's really big, right? So I'm just going to come back and I'm going to make sure that I conclude with some statement about my results.